sort of laid out the process here that we want to go through when we're looking for the absolute max or absolute min. And let's just kind of walk through those steps here with this example. So it says find the absolute maximum and minimum values of the function. F of x equals x to the fourth minus 2x cubed here on the closed interval -2 to 2. So remember that there's two things to look for. So the idea is that the absolute max or min may occur at a critical value or at an end point. Okay, so we'll find all the critical values and find the endpoints and then evaluate the function at those values. So the critical values, we'll take the derivative, set it equal to 0, and solve for x. Setting each factor out the x squared, set each factor equal to 0, get x equals 0 or x equals 3/2. Those are my critical values. And then we'll just plug all the critical values and the endpoints, all of these back into the original function. The endpoints were at -2 and 2. So here's our critical values. And here's our endpoints. And we just check which one is the biggest, that's our absolute max. Which one is the smallest, that's our absolute min. Okay, so let me check really quick. If I do f of 3/2 let's see, I guess something around -1.6875. F of 0 is 0. F of -2, let's see, what would that be? So that would be 16. And then let's see, 2 times 8 is 16, so plus 16, 32. And 16 minus 8, so 8. Or sorry, 16 minus 16, yeah, so 0 for that one. Okay, so looking at this, we can see where the absolute max occurs. That's at the highest value. So here we've got the absolute max. The absolute min occurs at the smallest value, which would be this one. Okay, so you see actually one of them occurs at a critical value, and then another one occurs at an end point. So just to kind of picture what we have here. See, at -2 it was 32, so something up here. F of 0 is 0. F of 3/2 is -1.687, so something down here maybe. And F of 2 is back at 0. So it kind of, kind of dips down to this point here, but then comes back. So that's where we have our absolute max here. and our absolute min here. Okay, so that's the process. We find the critical points, and then we plug all the critical points and the endpoints into the original function to see which one's the biggest and which one's the smallest. So, and yeah, here's the picture again. So here, let's try it with this example here. You've got g of x equals x to the 2/3 times 2 minus x. So actually what I might do here first before I take the derivative is distribute out the x to the 2/3. So you get 2x to the 2/3 minus x to the 5/3 when I distribute it in. So doing that first makes it easier to take the derivative now. Okay, so g prime would then be, let's see, 2/3 times 2 will be 4/3. X to the negative 1/3 when we subtract 1 from the power. And then here minus 5/3 x to the 2/3. Okay, so to find our critical values, we want to solve when this equals to 0 or where it's undefined. Actually, one thing I noticed is that we've got x to the negative 1/3. So one thing that maybe might help me is to simplify this a little bit. If I combine these together, I can get a common denominator. So I can multiply here by x to the 1/3 to the top and the bottom to get a common denominator. And so we can get our critical values just by setting the numerator equal to 0 and the denominator equal to 0. So 4 minus 5x equals to 0 when x is equal to 4/5. And then 3x to the 1/3 equals to 0 when x is equal to 0. Okay, so there's our critical points. Okay, so then we'll plug those back into the original. So we'll take g of 4/5, g of 0, but then we'll also evaluate at the endpoints. So we'll take g of -1 and g of 2. And then we'll see what we get in each of these cases. So let me do g of 4/5 on my calculator since it's a little bit easier. Something around 1.034. G of 0 will be 0, right? And let's see, g of -1 will be, I think 3, right? Because here, -1 to the 2/3 power is really +1 because you're squaring it and then taking the cube root. So that'll be +1, and then 2 minus -1 will be +3. G of 2 will be 0 because 2 minus 2 gives me 0. So it looks like here I've got 2 points that would be my absolute minimum. Right, see both of these points here would be the smallest point. And then this point here would be my max. Max, and then we've got 2 minimums. And actually what you notice is that the point here at x equals 0 is a point where the derivative is undefined, where it's not differentiable. So if we look at the graph here, I think in the next slide we have the graph. You see at x equals 0, there's like a corner there, a hard corner. Okay, so you see here's our absolute max here. And then we have these 2 points here that are the absolute min. Notice that this one's also a local min. This one's just an absolute min. All right, so here, let's look at one more example, kind of coming back to something that we've thought about in another section. So it says a stone is launched vertically upward from a bridge 80 feet above the ground at a speed of 64 feet per second. Its height above the ground t seconds after the launch is given by f of t equals negative 16t squared plus 64t plus 80. When does the stone reach its maximum height? So we can think of it like we're looking for the absolute max of this function on the interval 0 to 5. So we'll do the same process. Find f prime. Which will be negative 16 times 2, so negative 32t plus 64. And then 64 equals 32t, so t equals 2, I believe. So that'll be our critical point. So then we check what's the height at 0, at 2, and at 5. Okay, so you can see f of 0 would be 80. Which makes sense. That's where he's starting 80 feet above the ground standing on the bridge. So f of 2, if I evaluate 2 in our function here, we get 144 is the maximum height it reaches at 2. And then at x equals 5, I believe that's going to be when it hits the ground. So that would be 0. Okay, so this will be the maximum height. Makes sense, right? It starts 80 feet above, throws it up in the air, reaches the maximum height, and then comes back and hits the ground. Okay. So actually, to answer the question, when does the stone reach the maximum height? So it reaches the maximum height after 2 seconds. Okay. So I need to get started with the next section. And it's going to kind of think about something a little bit different, but I wanted to at least get the ball rolling a little bit with the next section. And we're going to look at what's called Rolle's theorem and mean value theorem, and then some consequences of those theorems. Okay, so the theorems themselves, I think say something kind of intuitive. So let's read what Rolle's theorem says, and look at the picture to help us understand what it's saying. It says let f be continuous on a closed interval AB and differentiable on the open interval AB, with f of A equal to f of B. So in other words, the endpoints have the same value. Then there is at least one point C in the open interval AB where f prime of C is equal to 0. So you can see why that might be the case here. Just looking at the picture, we're saying that the endpoints have the same function value. So they're both at A and B, they're both the same value there. So they have the same height at the endpoints. And then it's continuous and differentiable in between there. So you can imagine then we're connecting those endpoints with a smooth, continuous curve. So if it's got to pass through the same value at the endpoints of this curve, then somewhere in between it's got to have a slope of 0. So in other words, somewhere in between it's got to change directions, which is what we see here. Yeah, I have to draw this. So you know, try drawing it yourself. If I want to draw a smooth continuous curve that connects two endpoints that have the same function value there, well, there's only, there's a handful of things to consider, but really any smooth continuous curve that I draw here, whatever, has to have at least one point. Here in this one, actually, I can see that there's maybe more than one point where the slope would be 0, right? And sort of, I guess, so that's if I'm drawing a smooth continuous curve. If I just draw a straight line, well, then the theorem is still true because every point would be a point where the slope is 0, right? So you can see that with a picture, pictorially, this theorem seems to make perfect sense. And thinking about the continuity requirement, we can see that here, of course, that would be necessary because if I draw a curve that's not continuous, you could have like a jump in the curve where, yeah, if it's not continuous, then there's no point where the slope is 0, right? Because here it's got a point of discontinuity there, or here it's not differentiable. So there's a point where it suddenly changes slope, and so there's no point where the slope is 0. Okay, so these would be examples of why we need that requirement for continuity and differentiability. Okay, because if it's not continuous, then you could have there's no point where the slope is 0. Or here, if it's not differentiable, you could have no point where the slope is 0. So we require both continuous and differentiable in order to guarantee that it has at least one point where the slope is 0. So let's think about an example like this, just given the function f of x equals x cubed minus 7x squared plus 10x. And okay, well, first of all, we notice that it's a polynomial. So it's definitely continuous and differentiable everywhere because it's a polynomial. So basically any open, or sorry, any closed interval that I choose, it would satisfy those two conditions. But remember, we also require, part of the theorem is that we require f of a and f of b to be equal to. So we need to find a and b where f of a and f of b are the same, where they're both equal. So actually, we could probably think about factoring this guy to help us with that. I mean, there could be many different choices for a and b, but let's just think of what would be easy would be to find the zeros of this function. So find the values of x that make this function equal to 0. So I can factor out the x, and then we're left with x squared minus 7x plus 10. And then I notice that this actually factors into x minus 5 and x minus 2. So we'll see that at x equals 0, or at x equals 5, or at x equals 2, it'll equal to 0. So let's just choose an interval. So let's, I'm going to choose an interval from 0 to 5. Right? We see that f of 0 is equal to f of 5. Right? Because just plugging in those values here, we get 0. So we know, according to Rolle's theorem, there is at least one c in the interval, or I'll say in the open interval, 0 to 5, with f prime of c equal to 0. In other words, there has to be a point somewhere in between 0 and 5 where the derivative at that point is equal to 0. Okay, so so that's what we want to do for this question, is now find all points in that interval where f prime of c is equal to 0. Okay, so we'll take f prime now. (3x squared minus 14x plus 10). Set this equal to 0 and let's try and solve for x. And then kind of looking at this, I'm not sure if I can do this in my head or not, where we can just factor it, or not factoring it, then we can do the quadratic formula. Yeah, so trying to think of factoring in my head, I don't see any way to factor it, so I'm just going to do quadratic formula. So 14 plus or minus 14 squared and 96 minus 4 times 3 times 10.
Wouldn't that be 6 on the bottom?
2 times 3, yeah, good, thank you. Okay, so yeah, 196 minus 120 here leaves me with 76. So you got 14 plus or minus the square root of 76. Okay. So yeah, you can kind of see here there would be 2 points here, 14 plus the square root of 76 over 6, and 14 minus the square root of 76 over 6. My guess is that these are both going to be in that interval from 0 to 5. So let's check just to kind of get an idea of what these values are. So here this one would be roughly 3.78. And then this one would be, let's see, roughly 0.88. Okay, so here we actually have 2 points in the interval 0 to 5. Where f prime of that value is equal to 0. Okay. So if it helps here, you can imagine picture. You know, f of 0 and f of 5 are both going to be 0. Actually, you can also see that it passes through 0 at x equals 2 as well. So I guess 0.88 would be here in the middle there, right? And 3.765 would be, or sorry, 786 would be roughly right about there. So those would be the points where we have slope of 0. Okay, so maybe it's something like this. Okay. Or actually, I think I'm doing that backwards. It's probably going to be the other way around. So yeah, Rolle's theorem just gives us a way of determining whether or not these points exist, right? So the theorem tells us that, yeah, these points must exist. And here we can actually solve it out and we see that, yeah, there they are. Oh, here's the picture again. To kind of transition now to the mean value theorem, which says something a little bit more general. We'll look at the picture here first before we actually write out the statement of it to kind of help us picture it. So with the mean value theorem, what it really tells us is that if I have a function that's continuous and differentiable, sort of the same condition that we had in Rolle's theorem. But if we remove the extra condition in Rolle's theorem that the endpoints f of a and f of b are equal to each other, if we remove that condition, then the mean value theorem tells us that instead of saying that there has to be a slope that's equal to 0, it tells us that there has to be a slope somewhere in between a and b, where the slope matches the slope of the secant line from a to b. Right? So here in the picture, you see the green line here is the slope of the secant line from a to b. And then mean value theorem says that there has to be a point C somewhere in between a and b, where f prime of c, where the slope of the tangent line is equal to the slope of that secant line. So in other words, they're parallel, right? You can see that here this tangent line is parallel with the secant line. Okay, so the picture is exactly what we see here, where, yeah, any smooth continuous curve that I draw, when I draw the secant line between any two endpoints, there always will be a point in between, at least one point in between, where the slope matches the slope of the secant line. Right, and here you can think of maybe a variation of this would be, right, so again here, we're not requiring that the endpoints have the same height. And then I draw a smooth continuous curve that connects the two endpoints here. So according to mean value theorem, there should be at least one point in between where the slope of the tangent line is equal to the slope of the secant line. So here's my secant line connecting the endpoints there. And I can kind of see that, yeah, exactly 2 points in this case would have a tangent line with the same slope. Say maybe over here and over here. So those would be 2 points where it looks like the tangent line there and the tangent line there would have the same slope as the secant line. Okay, so it's sort of a variation of the picture that we see here. And you can see that, yeah, that it doesn't necessarily just need to be one point C. In this case, we could have multiple points, say C1 and C2. Right here, f prime of C1 and f prime of C2. You'd have 2 points there where the slope is equal to the slope of the tangent line here, or sorry, the slope of the secant line. So the secant line here so there's, yeah, so there's this conclusion that we can say that f prime of c must now equal to the slope of the secant line, f of b minus f of a over b minus a. So with that picture in mind, let's read what the actual statement is. It says, if f is continuous on the closed interval ab and differentiable on the open interval ab, then there is at least one point C in the open interval AB such that f of b minus f of a over b minus a is equal to f prime of c. Right? And again, this is our m secant. This is our m tan. So in other words, it's saying that the slope of the secant is equal to the slope of the tangent for some point in between.